So following on from the talk where we discussed enhancing the rate of natural attenuation using a technology called ORC, the oxygen releasing compound, to accelerate the rate at which microbes break down petroleum hydrocarbons in situ by adding oxygen to the groundwater. We then move on to how you can couple enhanced natural attenuation, you can refer to that as bioremediation, with absorption. So absorbing that contamination, in this case, to a colloidal activated carbon. Now, this has some advantages. While it is possible for us to look at a site, look at the contaminant mass and competing oxygen sinks, for example, and stoichiometrically work out how much oxygen you need to apply to the subsurface to reduce that contaminant mass in situ. It's very hard, though, for us to predict the rate at which that natural attenuation will occur. This is down to a number of different things. So as we had talked about previously, the contaminant type, what phase that is in, has a big influence, as does the hydrogeology for that particular site. However, one of the common themes, regardless of the site that you're treating, is down to the nature of the microbes themselves. So the microbes that are responsible for breaking down organic contaminants in the subsurface, they're not planktonic, so they're not like fish. They don't swim around in the aquifer seeking out contamination to metabolize, to eat. They are sessile. So what that means is they sit on the aquifer's surface and they secrete something called a biofilm. And it's this job of this biofilm to capture the contamination so that the microbe can metabolize it. So it has to wait for its food source to come to it. So they're actually much more like sea sponges. And to use this to our advantage, we've developed a number of colloidal activated carbon technologies. We have one called Plume Stop that has been out since 2014 and is primarily used for treating chlorinated solvents in situ, as well as PFAS plumes. Now, an evolution from this product is Petrofix, Petrofix remediation fluid that has been designed to treat high concentrations of petroleum hydrocarbons in situ. So it's a dual function activated carbon amendment that consists of finely milled granular activated carbon. So this has been milled down to 1 to 2 microns. So that's the size of a bacterium. That's the size of a pore throat. And what we've done is we have interpolated a slow release sulfate electron acceptor into that mix. And then we've also combined it with a second part of that product, an EA blend, so an electron acceptor mix, comprising nitrates and sulfates. So this can provide a rapid absorption of mobile contamination, so take that contamination out of the dissolved and in some cases free phase, and it can kickstart the rate of biological degradation. So it can kickstart that rate of natural attenuation. So it's been designed, as I said, to remediate petroleum hydrocarbons. So this includes BTEX compounds, fuel oxygenates, such as MTBE, gasoline and diesel range petroleum hydrocarbons, and a broad range of PAHs. Indeed, it works very well on PAHs. We are seeing it used on a lot of former gasworks sites here in the UK, for example. In terms of the challenges that Petrofix can help overcome with regards to biological degradation, there are 3 key ones. The first is high concentrations of hydrocarbons in the subsurface. So the challenge here is where you have excessive aqueous petroleum hydrocarbon concentrations, they can actually become toxic to the microbes that want to metabolize them. So a solution to this is to absorb that contaminant mass onto activated carbon. So you reduce the aqueous phase petroleum hydrocarbons to levels that are amenable to bioremediation. So that contaminant still remains bioavailable. The second then is the lack of terminal electron acceptors. So we touched on this in part 3 of this discussion, where we looked at enhancing the rate of natural attenuation. When a hydrocarbon is released into the environment, into the groundwater, the microbes that are in the subsurface will start to use up different electron acceptors. So they will go for oxygen first because it yields the most energy. They'll preferentially utilize that as an electron acceptor. We then go down the list of nitrate, manganese, iron, sulfate, and then finally you end up with methanogenic conditions. Now, with Petrofix, you can co-apply it with ORC. Indeed, a lot of the projects I have worked on have included that combination of technologies. It provides a really powerful solution to address higher levels of petroleum hydrocarbons in situ. But it can be used without ORC. If you're looking to yield just substantial betterment to the into the subsurface, so by that I mean a substantial reduction in contaminant levels, then you can use it with its nitrate and sulfate blend. Now, the benefits of this is that the nitrate as an electron acceptor is very readily utilized by the group of microbes that will preferentially degrade benzene. And it's benzene that's often the risk driver for groundwater cleanup of petroleum hydrocarbons. So if you can knock out the benzene early, it may be that you can quickly de-risk that plume. Finally, the other problem that comes with anaerobic biodegradation of petroleum hydrocarbons in situ is down to thermodynamics. So the aquifer under anaerobic conditions, as petroleum hydrocarbons are broken down, so your BTECs and TPHs are broken down by microbes that are utilizing nitrates and sulfates as electron acceptors. As this degradation is, as these compounds are metabolized, the microbes will produce waste products. This typically comprises organic acids such as acetate and dissolved hydrogen. And as those waste products start to build up, conditions in the aquifer become less and less thermodynamically favorable for the degradation of hydrocarbons to occur. However, under these conditions, we can create a syntrophy. So syntrophy just describes the action of two groups of microbes feeding together. So you get syntrophic biodegradation. What this means is, as these waste products are produced, a different group of microbes, the methanogens, utilize these waste products and degrade them, metabolize them through to carbon dioxide, water, and dissolved phase methane. So we have seen evidence, and indeed I'll talk you through a case study where after the sulfate and nitrate electron acceptors have been used up, you can still see evidence of syntrophy occurring. Finally, practical application. So of our technologies, Petrofix is probably one of the easiest ones to use. So what you can see here is the Petrofix concentrate being applied to water. Typically, we would mix it 5 to 7, between 5 to 1 and 7 to 1 dilution with water. You mix it, you agitate it to create this colloidal suspension, and then you can inject it into the subsurface. So it's very easy to handle and apply. In terms of its practical application, so you first dilute the Petrofix and then you add the sulfate and nitrate mix. Once you have created that mixture, you can pump or pour it into excavations. You can inject it via direct push injection or into standalone injection wells. But the key thing is, when it comes to the application of this product, is that you should do it under lower pressure. You don't need to inject this under very high pressure. In fact, it should be injected under low pressure, because what we want to do is to create an even distribution of this product in the subsurface. We want good interlocking radius of influence if you're injecting it down injection wells, or indeed down via direct push injection. So we get an even distribution of this product. We're not fracking it in to seams in the subsurface, so that you get an interlocking radius of influence, so you yield the best treatment possible. Here in the UK, we've seen it readily taken up by the spill response industry, and it's been used as a mitigation of a cross-site migration. So say you have a oil tank in somebody's back garden that has been spilt. People, different contractors are using Petrofix to stop that lateral spread of contamination, particularly under houses or close to sensitive receptors, so that they can then fully investigate the source of the contamination and undertake more targeted remediation. Similarly, it can be used to prevent off-site migration onto third-party land, just to keep, if it is an insurance claim, the administration of that job much more straightforward. Particle size and injection pressure are really two key important elements whenever you are thinking of engaging with a technology that you're injecting into the subsurface. Indeed, if you're looking to engage with a colloidal technology. So unlike other sources of activated carbon, be this granular activated carbon, which typically has a particle size between 400 and 1,000 microns, or even powdered activated carbon, which sits somewhere between 50 and 250 microns, you will need to frack that into the subsurface. Whereas with Petrofix, because you're dealing with very small particles in this colloidal suspension, you can inject this under low pressure, so you get an even distribution of the product in situ. Because you have this low particle size, you have this small particle size, it means that you can use it on sites where you have perhaps medium to fine sands, or even silts, and even more gravelly aquifers. If you were dealing with something like a clay, then chances are Petrofix wouldn't be an appropriate technology for you, particularly to inject. However, we do have other technologies that you can use in clays, principally being our controlled release electron donors and acceptors. In terms of when you are injecting this product, I appreciate that not every site you work on will you have delineated the flux zones or the more permeable zones in the aquifer. So what I always say is just keep an eye on the injection pressure as you're injecting it into the subsurface. If you see that injection pressure start to drop off, that would indicate to me that you've hit a flux zone, and it's really there that you want to concentrate your injection efforts so you can apply as much of that carbon as possible. It's also very easy to see where it has been applied. So from a single injection point, you can take a series of cores and look at black staining, and it may be that you're seeing a much wider radius of influence than we would have expected just looking at site data. So I touched on this earlier, application scenarios. So this can include tank replacements. It can include a series of barrier treatments to halt the off-site migration of contamination, protecting sensitive off-site receptors, or such as drinking water wells or rivers. Legacy sites for petrol filling stations, various applications within the spill response industry. I've had a series of sites actually where we have used this as a technology for vadose treatment to prevent the desorption and infiltration of contaminants into the groundwater, or it's used as a wider, as part of a wider integrated remediation treatment strategy. In terms of its performance, so this I'm going to take from a beta site that we did in the US. I like this as a case study because they really went above and beyond what is required to monitor for TPH degradation after Petrofix has been applied. So here they were looking at sort of secondary and even tertiary lines of evidence that we weren't just absorbing the contamination, but we were also kickstarting that anaerobic biodegradation process. So this site is in a place called South Bend in Indiana in the States. It was a former bulk petroleum storage facility that had a series of hydrocarbon plumes across it that had been subject to a series of remedial activities since 2006. So that included a pump and treat system and soil vapor extraction. However, following all of these works, there were still parts of the site where concentrations of TPH were high enough to warrant further cleanup, and we were asked if we could trial this new product, Petrofix, within some of these recalcitrant areas. So at first, Petrofix was injected into a small area in one of these recalcitrant zones of the site. And then based on the results, wider injection works were completed to address the other plumes elsewhere. So in terms of the results, so you can see here we were initially dealing with up to 33 milligrams per liter of gasoline range TPH and then 17 milligrams per liter of diesel range. After a single injection of Petrofix, you can see that these levels dropped pretty substantially, continued to. In February 2019, we saw a little bit of an upkick, but nothing like the baseline that we were initially dealing with. And certainly concentrations weren't higher than in August 2018, if you look at the diesel range TPH. However, by this time, based on the initial pilot results, the full-scale remediation works were approved and they were completed in April. And that then had a knock-on effect in May, where you see concentrations start to drop off again. It's a similar story with the BTEX, rapid reduction in contaminant mass, and then sustained reduction there afterwards. So in all, we saw a 94.5% reduction in contaminant mass. In terms of secondary lines of evidence, so as I said, they really did go above and beyond with the monitoring. Here they were looking at the uptake of the electron acceptor mix, the EA blend that was co-injected with Petrofix. You can see that nitrate and sulfate peak immediately after injection. You can see the steady decline of sulfate. That then kicks up after the April application. So you're starting to see some more sulfate in the system. What's key, though, is this evidence that syntrophic biodegradation is occurring. So after that sulfate has been used up, we still see sustained dissolved phase methane in the groundwater that would, again, suggest that this syntrophic degradation is continuing to occur after that sulfate and nitrate has been utilized by the microbes in situ. If you are interested in this, on our website, we have a series of sort of technical bulletins that really drill into this in a bit more detail. Finally, looking at microbial populations. So here we've partnered with a company called Microbial Insights to do quant array analysis, looking at the effect we had on the microbes post-injection. So you can see after that initial injection, from August through to May, the total cell count continued to climb above baseline. And really what's crucial is we're also seeing an increase in diversity. So we're seeing an increase in sulfate reducing bacteria, and we are also seeing a sustained increase in PM1, and that is a bacterium that is crucial to TPH degradation. So you can see immediately after the injection, there is a significant increase in the sulfate and PM1 cell counts, and then this continues through to May. So it's an interesting technology. It very much has its place on most petroleum hydrocarbon sites, if I'm honest with you, particularly if you are coming to the end of a remediation program and you have recalcitrant areas that you need to close out very quickly. Similarly, it can be used as a technology to stop off-site migration, or indeed I've done a few sites to stop on-site migration of contamination. So it is quite a versatile product, and indeed here in the UK it's been taken up incredibly readily, and indeed in Scandinavia as well. So you may have stuck with us through all four of these presentations, and you might be thinking, okay, it sounds interesting, but I need to get a handle on costs. And it's always the most common question that I'm asked is, how much does this all cost? So it's kind of like asking, how much does a site investigation cost? What does it cost me to do a cut and fill exercise? What does it cost me to remediate my site? It can vary wildly. Some people have tried to qualitatively or even quantitatively in some places try and answer this kind of question. I'd argue that they haven't done a particularly good job. I'd say this can vary wildly depending on each individual site. And it's why that site evaluation process is critical. It's why we offer a site review. We talk with you. We're very consultative in our approach to ensure that we are choosing the right technology for your site, both from a technical point of view, but also from a commercial point of view as well. And also, will this technology work? There's no point wasting your time and inside our time designing something if we don't have confidence in that it will work. If you are looking for some guidance, I'd say the Homes and Communities Agency did a pretty good job in 2015 illustrating how much and this can vary, and the different factors that can vary how much it costs to remediate a site. But something that we do try and do is be as transparent as possible. So on our website, we have over 200 case studies utilizing our technologies on multiple different sites, treating lots of different contaminants. Within these case studies, they are within this case study page on our website. They're all readily searchable. So you can search this by country, by products that you might be interested in using, so technologies of ours, the contaminant type, and even the previous or current industry of that particular site. So we try and make it very accessible for you to access. With these case studies, we try and give you as much information as possible, as succinctly as possible, and we'll look at the treatment area, the treatment cost, and the duration of the works. So most of our case studies, if not all of them, do highlight how much was spent on the remediation of that particular site. So you can look at these case studies and think, okay, this is maybe close to the ballpark that we're looking to that we have in terms of money to spend on that particular site for remediation, and then it can serve as a basis for you then to give us a call. So in conclusion then, injectable substrates can be used right across a contaminant plume, be it a combination of physical, chemical, and biological treatment. So it could be enhanced abstraction using Petrofix to accelerate the rate of natural attenuation in situ. It could be that we are dealing with the inner core of the plume. So it could be a combination of REGENOX, so that in situ chemical oxidant, with ORC, the oxygen releasing compound. And then finally, if you're looking to mitigate offsite migration of contamination, then you could utilize either ORC as a standalone technology, Petrofix as a standalone technology, or combine them together for a really powerful treatment to halt the offsite migration of contamination. That's everything. These are my contact details. Please feel free to connect with me on LinkedIn if you want to reach out directly. We in REGENESIS, we've got a whole team here of technical specialists that look at, well, we in the UK look at 30, 35 sites every month to review and give costings and strategies for. So if you do have a groundwater problem, please feel free to give us a call. If we can't help you, chances are we'll know somebody that can. So thank you for listening to this four-part presentation. I hope it was useful.